تمام. طبعا في الاول هحاول اتكلم شويه عربي وشويه انجليزي. العربي عشان البارتيسيبنت اللي معانا يبقوا فاهمين احنا هنتكلم على ايه، والانجليش هيكون بيسمرايز الجزء العربي. طبعا في الاخر هو ليه الحوسبه الكميه او ليه الكوانتم كمبيوتر يعني. وفي نفس الوقت الجزء الثاني هو ان الهاكاثونز هي بتستخدم كطريق ان هو يفوستر الايكو سيستمز او يقوي النظام الصناعي او النظام المجتمعي الخاص بالتكنولوجيا الكوانتم. ماشي، مبدئيا كده تو ورم اب عموما بقيه الناس يجوا، دي حاجه تي دي ال ار كده في الاول. انا دلوقتي بشتغل في عندي كده اكتر من بروفايل. اول واحد الريسيرش، واحنا بنحاول نشتغل في الريسيرش على كوانتم انفورميشن وكوانتم ماشين ليرنينج وكوانتم كيمستري. في الاديوكيشن مفيش ترانسليشن يعني نشتغل انجليزي على طول. تمام. And educator, like as a quantum education officer at Amsterdam University of Applied Sciences and co-founder of iCafe, an online platform to teach quantum computing and AI. I also have entrepreneurial level, and we have a startup called Molkit. It's Molkit SaaS, so it has been established in Paris. تم إنشائها في باريس. And this is a quantum computing and quantum AI consulting and software company. We are now part and a member of QUIC. This is the European Network of Quantum. احنا أعضاء من المنظمة بتاعة الكوانتم بتاعة الاتحاد الأوروبي. And QEDC, and this is the equivalent US version of QUIC. And those also have Google and other international companies abroad. And I also have science communication, so we do like tech YouTube videos to introduce complex topics in a simplified way. لما جيت بدأت الدكتوراه كان في مشكلة خطيرة. هنحاول بس اتكلم جنب المايك كده. لما جيت بدأت الدكتوراه كان في مشكلة خطيرة عندنا، وهي ان الحسابات اللي بنستخدمها the computations that we are doing during the PhD work takes very long time. بياخدوا وقت طويل جدا. Can eat up few months, even up to 6 months to run one full simulation. بياخد حوالي 6 شهور عشان يرن full simulation. المشكلة اللي موجودة هي ايه؟ ان كان الشغل كان على جيمس ويب سبيس تلسكوب، وجيمس ويب ده واحد من التلسكوبات اللي طلعت في الفضاء عشان تانلايز. جيمس ويب سبيس تلسكوب كان واحد من التلسكوبات اللي طلعت عشان تديتكت البريزنس اوف اورجانيك مولكيولز ان انترستيلر ميديا، عشان تديتكت المولكيولز دي اللي موجوده في الانترستيلر ميديا. والمشكله كلها احنا ما فيش حد يقدر يسافر بقى ويعدي كم مليون سنه ضوئيه عشان يعرف يروح للمكان ده. It's very distant celestial objects. فالحل الوحيد to analyze the spectra. والspectra from the spectra we can identify the fingerprints of the molecules and even the abundances of these species. كمان كمياتهم قد ايه في الفضاء عامله ازاي. وطبعا جيمس ويب هو واحد من الادفانسد تلسكوبس اللي كانت موجوده، بيقدر يديتكت في النير اند ميد انفراريد اوبزرفيشنال كابابيلتيز، وبيقدر يشوف حاجه بنسميها بروتو بلانيتري ديسكس. بروتو بلانيتري ديسكس دي السحب الكونيه اللي طلعت منها الكواكب او اتنشأت منها الكواكب على مدار ملايين السنين. نقدر نتخيل ان نشأة الكواكب اللي احنا بنشوفها طلعت بالفعل من quantum mechanical effects. The planets started just from quantum mechanical collisions that happen between molecules. بدأت من النظام ده and then sparked life, and sparked the all existence of organic species. فكان الفكرة كلها ان في gigantic clouds بتبدأ تكولابس لحد ما تفورم الانترستيلر ميديا او البيتزا شيبت كلاود اللي احنا بنسميها بروتو بلانيتري ديسكس. جوه البروتو بلانيتري ديسكس بتطلع كواكب، وبتطلع في النص شمس جديدة كده بنسميها بروتو ستار. And from the protostar, due to the conservation of angular momentum, the whole system starts to spin very fast due to the conservation of angular momentum, and then it flattens. بيعمل بقى شكل البيتزا كده. And بعد وقت طويل بتبدأ الكواكب تتكون. طبعا ده أنا مش هدخل على level of details. I'm not gonna discuss the level of details of this equation, but we all start from first principles, all Hamiltonians, and these Hamiltonians describe how molecules interact and collide at the most fundamental level in these interstellar media. الجزيئات بتصطدم ازاي، بنوصفها بهاملتونيان. وعشان نحلها بنستخدم بقى كيرنلز كبيره جدا. الكيرنلز دي بتاخد وقت طويل. فمن هنا انتوا بتشوفوا البروبلم بتاعت الكيمستري جايه منين. البروبلم بتاعت الكيمستري او الفيزيكس سيميوليشن they emerge from the need to do full simulations that include very large computational space. يعني هم جواهم الفضاء الخاص بالحسابات كبير جدا. وده مثال احنا بنشوفه لو احنا عندنا 100 معادله بنحلهم. If we have 100 equations we need a half a second to solve them. 300 we get about 4 seconds, and suddenly it scales up to 6,600 seconds if we have around 5,000 equations. And you see a pattern that's close to the exponential. عندنا دلوقتي باور 3 بس بعد كده بيدخل على الاكسبوننشال. ولو انت هتضم بقى مولكيولز كل ما السايز بتاع المولكيولز gets bigger الكومبيتيشن بتكون مور اكسبنسيف. فمن هنا كانت هنعمل ايه طيب؟ يعني هنوصل لفين؟ ففي كلاسيكال كمبيوتر سوبر كمبيوترز بتستخدم وكنا بنستخدمها في وقت الدكتوراه عشان نعمل السيميوليشنز دي. بس كانت المشكله ان برضه ستيل عندنا ليميتيشنز. وي هاف تو دو ابروكسيميشنز. فجه البروميس لما كنت في سنه ثانيه درست كوانتم انفورميشن في الماستر. فكان المشرف بتاع الدكتوراه بتاعي كان بيناقش بيقول طب ما احنا ممكن نحاول نبروجكت الكيمستري على الكوانتم كمبيوتر ونحاول نسولف ده بطريقه efficient. طب نعمل ايه بقى على الحكايه دي؟ طبعا الترانسليشن ما بين الثيوريتيكال كيمستري والكوانتم كومبيوتنج واحده، الاثنين زي بعض بالظبط. يعني في ناس كتيره كوانتم انفورميشن ساينتست كان بيشتغلوا ثيوريتيكال كيمستري، فالسويتش كان يعني ايزي خالص. فقعدنا نفكر طب هل نقدر نرن كل الحاجات دي الابلكيشن الخاصه بالمولكيولر ديزاين، ماتيريال ديزاين اند دراج ديزاين. ومن هنا بقى في السنه الرابعه بدات اسويتش ناحيه الكوانتم كمبيوتر. Quantum computing it has this phenomenal power due to the ability to have a superposition. لو انت عندك عربيه راكنه كده ماركه مثلا فيات او اي حاجه، وعندك مثلا عربيه سريعه جنبها زي مثلا لامبورجيني او اي عربيات من العربيات بتاعه فورمولا 1 موجوده جنبك، الاثنين في شارع صغير هيمشوا بنفس السرعه بطيئه، بس واحده فيهم لما تطلع على الطرق السريعه في المانيا بتاعه الاوتوبان هتروح قرب ال 500 كيلو في الساعه، والثانيه مش هتعرف توصل للليفل ده. فمن هنا الكيوبيتس هي الوحده بتاعت الكوانتم انفورميشن في الكوانتم، وهي اللي بتعدي الكلاسيكال بيت لان عندها الابيليتي تو بي بريزنت ان 0 and 1 at the same time. ده الشكل السينمائي. طبعا بحب حي طبعا اي بي ام على الصوره الجميله اللي هم واخدينها دي سينماتيك فيو. سيستم 1 طبعا ده القديم طبعا، بس هي صوره يعني سينماتيك كده حلوه للفريج اللي معلقينها كده. شكله حلو والله. دي حقيقه فعلا. فمعنا الدكتور احمد. فده بعد الصوره السينماتيك دي لو احنا عملنا زوم ان جواه هنلاقي ان في حاجه شبه دي موجوده كده. دي الفريج اللي موجوده بيبقى فيها سوبر كوندكتنج كيوبيتس. فلما بنيجي نعمل حسابات في الكوانتم بنضطر نترجم الخوارزميات اللي احنا بنستخدمها كلاسيكالي على الطريقه اللي ممكن ترن على الكوانتم. We need to translate our thinking and map the classical algorithms into quantum algorithms to be able to run it on quantum computers. And to do so we need to map them on the language or sequence of gates. ممكن بقى الجيتس دي تو بي جروبد، نعمل بقى اوبتمايزيشن، بس في الاخر احنا بيكون عندنا ريجستر اوف كيوبيتس بنحط سيكونس اوف جيتس وبعدين بنميجر عشان نحول المعلومات من الكوانتم وورلد للكلاسيكال. فمن هنا بنبدا نتريف المعلومات دي عن طريق الاوبزرفابلز، وبعد كده بنحصل على المعلومه. فالسؤال بقى دلوقتي ازاي بقى نستخدم الكوانتم كومبيوتنج وازاي بنستخدمها عشان نعمل الحسابات. التفكير الحالي دلوقتي احنا عندنا الفول ستاك ابروتش. انت محتاج مالتي لاير ثينكينج عشان تترجم المساله اللي عندك، والمالتي لاير ثينكينج ده معناه ايا كانت اليوز كيس بتاعتك سواء في اللوجيستكس او الفاينانس او البورتفوليو اوبتمايزيشن او كوانتم سيميوليشن وكيمستري او باتري ديزاين او دراج ديزاين او هيلث كير، كله في الاخر لازم يتعمل له مابينج لبروتوكولز او فورماليزم معين كان بي اكسكيوتد اون ذا كوانتم هاردوير. والمابينج ده معناه ممكن يبقى اوبتمايزيشن بروبلم، ممكن يبقى في الاخر هاملتونيان فايندينج جراوند ستيت اوف بارتيكولار هاملتونيان، او مثلا حل مثلا ماكس كات بروبلم بانك بتفايند مثلا البيست تراجكتوري لبروبلم. طيب دلوقتي دي الحسابات وده المتوقع من الكوانتم. الكوانتم has a promise to deliver very fast computation. Of course, the quantum advantage every time is being the definition of quantum advantage is being upgraded. Clark is laughing here because he also has his own thoughts about the quantum. But the quantum advantage is now about the speed, but not only speed, it's accuracy also. How much precision you can get from that. How much power you can get or how much information you can get from running the quantum simulation. فمن هنا الكوانتم ادفانتج كل الناس بتحطها فقط على السرعه، لا هي coupled مع الاثنين. فعندنا دلوقتي different types of quantum hardware. احنا اللي شفناه قبل كده كان اي بي ام كوانتم، ده السوبر كوندكتنج تايب، وطبعا هو موجود افيلبل على الكلاود. واي بي ام طبعا عندها اوفرنج للكلاود سيرفيسز الخاصه بالكوانتم، وتقدر تاكسس اكتر من باك اند. في انواع تانية من الكوانتم كمبيوترز متاحه في الماركت، زي مثلا الفوتونيك تشيبس، عندنا الالترا كولد اند نيوترال اتوم كوانتم كمبيوتر، وعندنا كمان توبولوجيكال لسه طبعا في التطوير، وعندنا حاجه اسمها كات كيوبيتس، مثلا امازون ويب سيرفيسز كانت اعلنت عنها. مش هندخل طبعا في الشرح لكل واحده عندها الثيوري بتاعتها. وعندنا الايون تراب تكنولوجي. في تكنولوجيز كتيره جدا متاحه في الماركت، في منهم بقى ماتيور، وفي منهم اللي لسه ان ديفلوبمنت، يعني لسه قدامه شويه عمان ما يبقى ماتيور اند ماركتبل، ولسه في حاجات ستيل ان ريسيرش زي الموليكولار كيوبيتس مثلا، او بعض الكيوبيتس الثانيه اللي ممكن تكون جود كانديديت، لكن لسه في الفيز بتاع ريسيرش according to the public domain knowledge، لان برضه في حاجات لسه شغاله في الستيلث مود، شغاله في ريسيرش او لسه مش معلن عنها، فشغاله في المجال، فممكن يتسمع عنها بعدين لما يحققوا حاجه. وفي حاجات بالفعل كوانتم كمبيوتر موجوده في السوق، زي مثلا سبين كيو عندها ام ار اي كوانتم كمبيوتر، هم عندهم عدد قليل من الكيوبيتس المتاح حاليا في الاجهزه بتاعتهم، وتقدر كمان ترن الكوانتم على سيميوليتورز. وفي حاجات اوبن سورس كمان كوانتم كمبيوترز، يعني الاركايف مليان بيبرز وحاجات تفولو. فاحنا دلوقتي عشان الباشن يطلع في الكوانتم، خصوصا في البابليك اوتريتش، في اي كوميونتي بيلدينج لازم يبقى فيه اهتمام بالكوانتم، والناس تبقى اوير يعني ايه كوانتم وايه الدليفري اللي ممكن يتم منها. والكوانتم مش بتساهم فقط في الاكاديميك ريسيرش، ولكن كمان في الاويرنس عن التكنولوجي او الهاي تك ان جنرال. فمثلا على سبيل المثال عشان نوصل في الهاكاثون بقى، كان في مثلا بنعمل مانثلي سيريز مع المكتبه، كان بيبقى فيها انفايتد سبيكرز من كل مكان، وكل شهر بيكون في ناس بتتكلم، بيبقى في سيم معين او في توبيك معين بيتعملوا فيتشرنج. وبعد كده بدانا نتكلم على يبقى عندنا ويكلي اكتيفيتيز، والويكلي اكتيفيتيز دي مثلا زي كوانتم اي اي لاب اتكلمنا عنها كنا في محاضره هنا ايرلير في ابريل في المكتبه. بدانا نتكلم على البيلدينج كوميونيتيز في الكوانتم اي اي، وازاي مثلا ان البيلدينج كوميونتي في الكوانتم بيساعد في الورك فورس. وبعد كده عشان نبدا نستعد للكوانتم والاويرنس يزيد، بدانا نبدا نشتغل على فكره ازاي بقى نتعلم فكره الهاكاثون، والناس تبراكتس الهاكاثون فعملنا مثلا اكتيفيتيز كتيره زي مثلا كوانتم سمر سكول، الدراي ران، وهكذا. في نقطه حابب اركز عليها هنا، ان الكوانتم عندها البروميس تو ديليفر ده، بس الفكره كلها ان هو علم صعب جدا ومش سهل. يعني هو it needs some time to digest all information and the knowledge. And for that, the knowledge is not only like a textbook knowledge, it's also about understanding the news, about the technology, how to perceive them, how to distinguish between fake and hyped and also authentic news. That's also need some culture، يعني ده بيحتاج ثقافة وبيحتاج approach، الناس تبقى ملمة بالحاجات دي كلها. وعشان كده حضور التوكس وحضور الأنشطة بيخلي الناس تبقى up to date بالنولج. واحنا في شركات كتير على مستوى العالم including IBM بيعملوا شغل جميل جدا على مستوى العالم في مجال التريننج، في مجال الهاكاثونز، في مجال السمر سكولز، في الحاجات دي كلها. فكل ده بيضيف للمجتمع. وكان في الدراي ران مثلا كان عندنا مسائل مهمه زي مثلا استخدام الكيمستري فور اتموسفيريك ابلكيشنز، الويذر فوركاستنج، وعندنا كانت مساله ماشين ليرنينج للديسكفري بتاع نيو اركيولوجيكال سايتس. وكان في ناس طبعا فازت، وكان في كوميونتي طلع جديد لحد ما بدانا نوصل للبريبريشن بتاع الهاكاثون بتاع النهارده. في حاجه تانية حابب اقولها، ان الاكتيفيتيز بتاعت الكوانتم على مستوى العالم ساهمت في انكريز السكيل سيت بتاعت الورك فورس من 10 ل 15% according للهايست كونسلتنج كومبانيز زي ماكنسي كده على مستوى العالم. فده معناه ان كل ما بيكون عندنا هاكاثونز زي دي او ايفنتس زي دي، ده بيساعد في زياده المعرفه وزياده المهارات، مش في مجال الكوانتم فقط. عشان كل الناس بتقول طبعا انا لو هشتغل في الكوانتم هدرس ايه؟ what I can do with quantum knowledge. Now, you can do a lot with quantum knowledge because it's not only echoed or reflected on the quantum tech, but also can be used and recycled in semiconductor industry, in the semicon, but also in the photonic, in the communications, and in many fields as well. يعني النولج نفسها والمهارات ممكن تستخدم في معرفة تانية. وفي ناس كتيرة من الكوانتم كومبيوتنج عملوا شغل كويس جدا في السيميكوندكتور، وكانوا very good architect they did very good work in semiconductor industries. وعشان كده بدأنا نوصل النهارده للهاكاثون بتاع النهارده اللي هو طبعا أول هاكاثون قومي في مصر first ever national quantum hackathon. وبدأ يبقى معانا تيم من المنتورز يبقوا موجودين. التيم ده عمل شغل جميل جدا، والشغل ده كان ايكوت في مراحل كتيره وسيكونس كبير على مدار الرحله بعد ما فكرنا في موضوع الهاكاثون من سنه ونص كده. عمل شغل جامد، خصوصا كمان كان في ناس جراديويت من الكوانتم اي اي لاب الويكلي سيشنز اللي موجوده وبداوا يساهموا. في ناس جم البروفيشنال ماستر عند الدكتور احمد يونس يساعدوا معانا. وحقيقه كان في كوميونتي فايبرت كوميونتي من السمر سكول ومن كل الاماكن دي بداوا يجتمعوا، يبقى في تيم من الفولنتيرز فعلا عايز يساعد مع المكتبه. وطبعا المكتبه مشكوره مع كل البارتنرز انها عملت المجهود الرائع ده، والتيم طلع المجهود الجميل ده. انا حابب ارفلكت دلوقتي على التيم، مش هدخل بقى في شرح التكنيكال، هتكلم على التيم كمان دقيقتين لان هو برضه هيطلعوا يتكلموا معانا. حابب اتكلم على حاجتين. احنا دلوقتي عندنا 3 تشالنج موجودين في الهاكاثون. We have 3 main categories of problems. First one is about optimization, and the second one is about how to use quantum machine learning to make a prediction. And the prediction now is for a neurological disease. And then we have the third problems about the chemistry optimization, our chemistry solution for carbon capturing. Of course, this problem inspired by our colleague here, Dr. Ahmed Al-Qatacha, also proposed in one of our calls مع Dr. Ahmed Yunus والباشمهندس Yusuf to talk about carbon capture. Then we have this problem in our radar now. It's one of the problems in the hackathon. كان عندنا الاوبتمايزيشن دايما بيتكلم برضو عنده الدكتور هشام والاساتذه الافاضل التانيين موجود معانا، وكان موجود معانا في الدراي ران. وعندنا كمان الكوانتم ماشين ليرنينج ابروتش. ف we have 3 main categories in the hackathon, and then we have very vibrant and excellent jury members and the speakers who are also gonna judge and assess the final presentation in the final day of the hackathon on Friday, where everyone basically should wrap up all the presentation and present their findings. لازم يقدموا كل الكلام ده ويقدموا الشغل بتاعهم in a specific format that will be announced today by the mentors. دلوقتي حابب انفايت التيمز بتاعه المنتورز عشان نبدا نتكلم على ازاي احنا عملنا الديزاين بتاع الراوند دي من الهاكاثون، وكمان نديهم فير كريدت للناس اللي شاركت في التنظيم مع المكتبه. فهم الناس بقى تيجي تستيب اب هنا. معلش يا جماعه قومناكم بقى من كراسيكم، ما علينا عادي. وحقيقه طبعا عندنا تيم عمل شغل جميل جدا. Very excellent work in the dry run hackathon, the trial hackathon that we have performed, and that was very successful round of the hackathon because we have learned a lot about our participants, but also the participants have learned also about the culture of hackathon. هو كان تعليم متبادل، يعني احنا كلنا كنا بنتعلم من بعض. وكان عندنا بعد كده as a second preparation we had like a very quick summer school to prepare them and set the baseline and the benchmark level for the challenges. ودلوقتي انا هدعو البعض من الزملاء يبداوا يتكلموا. احنا عندنا دي اول صوره للناس، في طبعا منهم اللي موجود معانا دلوقتي وفي اللي اعتذر لظروف اجتماعيه او عائليه. وهذا دلوقتي نبدا نتكلم على الستاتستكس. فاحمد.
مساء الخير. الحقيقه احنا على مستوى المشاركين وعلى مستوى المنتورز وعلى مستوى كمان المشاركين اونلاين كان حابين يكون عندنا تنوع على كذا دايمنشن، من ناحيه ان هم كمان يبقى في تنوع في الجندر، تنوع في المستوى الاكاديمي، تنوع في التخصصات، تنوع كمان في البروبلمز اللي هم مهتمين بيها. لو هنتكلم الاول عن منتور، عندنا 17 منتور موجودين النهارده معانا. زي ما احنا شايفين يعني التمثيل متوازن شويه، ممكن بعض الفيميلز اعتذروا كانوا المفروض يبقوا موجودين. التخصص بتاعهم مختلف شويه، فهنلاقي عندنا كمان باتشلرز وبي اتش دي بوست دوك مختلفين المنتورز. ممكن الباتشلرز نحس ان هم بيساعدوا في تحسين التجربه للمشاركين لان هم اقرب ليهم في السن، معاهم في نفس المستوى التفكير، فده بييفولف الهاكاثون بصوره كبيره. احب يعني اتكلم الاول عن المشاركين وتنوعهم. هسيب ساعتها فرجاني يتكلم عن التنوع ده.
ماشي. وممكن بعد كده طب محمد نكمل بقيه الكلام. عندنا تنوع برضو طبعا في الجامعات هنا موجودين almost 19 جامعه represented، وعندنا محافظات كتيره قوي represented موجوده. فكان فعلا السelection criteria كان بتساتسفاي ال OQI criteria. we make sure that the diversity is fulfilled and has been achieved, and also the diversity also of knowledge, background and universities. اتفضل.
مساء الخير. واحنا كان الهدف بتاعنا عامة ان احنا نحاول نوزع التيمز جغرافيا وتكنيكال ويونيفرسيتيز، بحيث ان احنا نعمل فرايتي ونعمل دايفرس كده بين التيمز، بحيث ان هم يبداوا يعرفوا يتعلموا ازاي يشتغلوا از تيم حتى لو ما يعرفوش بعض، ويبداوا يتعلموا ازاي يدخلوا تشالنجز من غير حتى ما يعرفوا اي باك جراوند عنها. ودي كان الهدف بتاعنا، ان احنا خليناهم بعد ما قسمنا التيمز بالشكل ده خليناهم يدخلوا ديسكشن كده ان هم ازاي يختاروا البروبلمز بتاعتهم. فدي كانت اول تاسك تقريبا يعني عملناها. فطبعا فكان عندنا بعد
ممكن بس ندعو المنتورز الاجانب. Can we invite can all our foreigner and Arab and also our foreigner mentors to come here? We have also mentors from the States, and we have from different Arab countries, from Lebanon and from Morocco, and also from Emirates are joining us in the mentorship team. Okay, so yeah, big clap for them.
الحقيقه هم عملوا مجهود يعني عظيم جدا في سمر سكول، خصوصا جيمس في الماثماتكس، وليد في الكوانتم ماشين ليرنينج، وكانت حاجه ممتازه جدا، زياد في الكيمستري. الحقيقه كل توبيك من اللي احنا موجودين النهارده في البروبلمز كان ليها يوم مخصوص في السمر سكول، وده كان تاهيل كويس جدا. كان جزء ثيوريتيكال، جزء لاب.
طيب انا كمان حابب ان انا اقول ان احنا بنعمل كمان السيشن ده عشان كمان to know your mentors who are gonna work with you in the teams، فعشان يعرفوا الفرق اللي انتوا شغالين معاه. طب زياد ممكن تدي كومنت على السمر سكول قبل ما نقدم اور يعني جيست منتورز؟
مساء النور. في الكوانتم سمر سكول كان حصل قبليها اللي هو الدايران هاكاثون، فاحنا كنا عملنا اناليسيز للتيمز هم بيقدموا برزنتيشن وكودنج سكيلز بتاعتهم. لقينا ان هو في بعض النواقص في العلم او في النوليدج او في التكنيكال سكيلز والساينتفك سكيلز، فدي قلنا لازم نبلد عليها عشان يبقى جاهزين للهاكاثون الجاي. فعملنا الهاكاثون على 5 ايام بحيث ان هو يبلد للبروبلمز بتاعت الهاكاثون. والبروبلمز بتاعت الهاكاثون كان 3 انواع: كوانتم ماشين ليرنينج، كوانتم كيمستري، كوانتم اوتومايزيشن. فاول يوم كنا ركزنا على الماثماتكس والباك جراوند بتاعت الماثماتكس، وكان معانا دكتور جيمس بيشرح لينير الجبرا، وبعد كده دكتور طاهر شرح معانا داتا اناليسيز. وتاني يوم ركزنا على الماشين ليرنينج، وكان باشمهندس عبد الرحمن هو اللي قام بالواجب. وتالت يوم كان عندنا كوانتم ماشين ليرنينج، ودكتور نهيل ودكتور وليد شرحوا مواضيع يعني فيها. ورابع يوم كان معانا دكتور ندى شرحت كوانتم اوبتمايزيشن، وانا كنت شرحت كوانتم اوبتمايزيشن برضه. وفي خامس يوم او اخر يوم كان دكتور طه شرح كوانتم كيمستري، وانا برضه معاه كنت لايف في كوانتم كيمستري. فاحنا حاولنا نخلي الناس تستعد بشكل كويس للبروبلمز، بحيث ان هم يعملوا جود سولوشنز وجود ساينتفك ميثود.
شكرا زياد. Then we can have a word from our guests. عرف نفسك كده.
Yeah, thank you very much for the invitation, of course. And yeah, it is very good initiative to have like this hackathon in Egypt, and really important to focus on these 3 axes, like promising areas like quantum chemistry and quantum simulation, quantum machine learning. So yeah, and also like starting this from an Arabic word is very promising, very important for the Arabian region, and specifically also for Africans is also very important. Yeah. So what else to say is looking forward. The teams are really working hard. I guess they already started like from yesterday, and they're doing some progress. And we're looking forward to orient them and give them help whatever we can do from resources and technical helps. Yeah.
James, and very short word.
Marhaba. I'm learning. So,
Good progress.
so I'm here to help mostly with math, but my team will hopefully benefit in a few ways from some conversations that we'll have. And anyone here is welcome to ask me anything about math at any time, and I'm happy to talk. So I am very happy to be here. I met Yusuf at the Hackathon in Abu Dhabi in this past April. I don't see him right now, but we spoke, and then he said, "Oh, I'm going to put on this hackathon in Egypt, and maybe you would be interested." And I said, "Sure," and then we kept in touch, and so here we are. And I have Amro to thank for even introducing me to this entire ecosystem, because I was a mentor at some other event back in New York, and then that led to this sort of whole avenue. And it's exciting and wonderful to work with all of you, and I look forward to what will be achieved this time.
Yeah, thanks, James. Nohaila.
Hi everyone. Thank you for the invitation. I'm pleased to be here, and I'm very happy. Usually, I already supervised or mentored for different hackathons, from UAE to Lebanon to here. So it's very nice. And every time, you just explore new ideas and meet new people and the way how they work. But I would just say, probably Walid and James, they said almost everything. But I just want to highlight something. It's always after the hackathon. So, okay, you start a project, most of them, they are not familiar with quantum. They are open to this new paradigms. They explore it, but it's better to keep exploring after the hackathon. And based on some experience, we have some students or that becoming from masters or from bachelor to PhD, that they are just focusing and working on quantum because of those hackathons. So yeah, so sometimes the hackathons, it's a good, I don't know how to explain it, but it's good. It gives you more opportunities and more chances. So for me, during my PhD, I was mentoring different teams during the NYU, New York University, Abu Dhabi hackathon. And then I think I joined for 2 years. Then in the third year, I joined or the fourth year, I joined as a postdoc there. So I was doing my PhD in Morocco. Then I was traveling to NYU just to mentor a team. Then after that, I built connections and start working on or focusing more on quantum. Then I end up by working there. Yeah, sorry about that. Yeah. So it's just I want to highlight that the hackathon, it's always after the hackathon. Just okay, don't think of it it's just a project, but keep exploring after that.
Okay, thanks, Nohaila. And big clap for Nohaila. Okay, Jad.
Hello, I'm also very happy to be here. Like James, I met Yusuf in Abu Dhabi, and he told me about this hackathon, and again, here we are. I think the important thing about these hackathons is building a community and empowering future students to be able to do something that's different. I think this is how we build driving forces, especially for us in our Arab world and the Middle East as well. We need to do these kinds of things to foster connections and to start empowering our students to do these things. And at least for me, this is what empowered me to be able to do other things around the world. And I'm really happy to be here to be able to learn how to be a mentor and to give that to other students as well. Thank you.
Yeah, thanks, Jad. We'll have a quick sentence from Ahmed El-Fiqi about the Dry Run Hackathon.
في البداية أنا حابب أن سعيد جدا بوجودي هنا معاكم. في البداية بدأت المشوار مع دكتور أحمد يونس بمحاضرات تعريفية في تبع كيورلد وكيو ايجيبت. الشباب كان على قدر المسؤولية وشباب كتير انضموا للمحاضرات دي وكانوا مبسوطين جدا بتعريف الكوانتم كومبيوتنج في مصر وفي على مستوى الشرق الأوسط. بعد كده بدأت الرحلة مع الدكتور طه سليم في الكوانتم AI لاب من 4 شهور اللي تقريبا ادينا 4 أو 5 محاضرات تعريفية عن الكوانتم كومبيوتنج والكوانتم الجوريزم والكوانتم بروتوكولز. أنا شايف إن التفاعل فيها كان جامد جدا من الطلاب واستفادوا والناس أشادت بالمحاضرات دي. بعد كده بدأنا إن شاء الله بدأنا مع الدكتور طه الدراي ران هاكاثون. بدأت في محاضرة تعريفية عن الكوانتم كومبيوتنج واستخدامه وأهميته في الريل وورلد تشالنجز. بعد كده على مدار 3 أيام كان في دراي ران هاكاثون، كان في 3 بروبلمز كانت عن الكوانتم ماشين ليرنينج والكوانتم كوانتم كيمستري سيميوليشن. الشباب كانت متفاعله، الحقيقه كانت متفاعله، كانوا على قدر من المسؤوليه، وكان عندنا 3 وينرز تيمز. شكرا لحضرتك.
شكرا يا احمد. ناخد بقى دكتور اسماء، الخير بقى والبركه بتاعت التيم يا دكتور اسماء وزاز.
وأنا في الآخر حابة أشكر اللي هم بسميهم الجندي المجهول للموضوع كله. لا هو بصراحة يعني جيت أعمل برزنتيشن عن الجورني بتاعة الهاكاثون، لقيت البداية فعلا كانت من قبل ما احنا نظهر بكتير، يعني مع المهندس يوسف ومع دكتور طه. حقيقي هم قاموا بمجهود كبير قبل ما نظهر احنا في الصورة، احنا ما كناش نعرف أصلا الموضوع يعني. فشكر كبير ليهم على ان هم بصراحه ساهموا في ان الهاكاثون يقام لغايه بالتايم اللي هم حددوه فعلا على الصفحه. كل حاجه تمت في ميعادها وتمت على اكمل وجه. حابه اشكر الطلبه، احنا ضغطناكم جامد بصراحه، ضغطوا كتير من الاو كيو اي التريننج، وبعدها على طول سمر سكول، ما كانش فيه راحه خالص. وحقيقي المجموعه دول خيره الشباب اللي احنا اخترناهم، كانت الكرايتيريا اللي اخترنا بيها كانت صعبه فعلا، وان شاء الله انا واثقه فيهم في يوم المناقشه ان هم هيأدوا اداء جيد، وانتوا هتنبسطوا منهم باذن الله يعني. بشكركم وبالتوفيق.
شكرا جدا دكتور اسماء. لا خلصت ماشي. معانا بقى هيبقى في تعريفات سريعه، وبعدين هنختم بالبشمهندس احمد سليم. كان معانا برضو مشارك معانا في الدراي ران كسينيور جادج، وكان حقيقه مدي فيدباك جميل جدا، ومشارك معانا في التنظيم بتاع الدراي ران. هنختم بيك على فكره، خلي بالك.
I'll keep it quick بسرعه.
ماشي.
طيب انا شرفت طبعا ان انا اكون جادج في الهاكاثون دراي ران، وعندي 2 يعني زي ملاحظتين. الاولانيه الشباب والدايفرستي اللي كانت موجوده، كان موجود في الدراي ران ناس هاي سكول وبوست جراديويت وجراديويتس، والحماس اللي احنا شفناه من الشباب اعتقد ده الليدرز ان شاء الله هيكونوا المستقبل في الجزء بتاع الكوانتم. وملاحظه الثانيه ان كان في ناس لاول مره يسمعوا عن الكوانتم، والاصرار الغريب اللي احنا لقيناه في الفاينل برزنتيشن، الناس قدموا نتائج كويسه جدا، واستفادوا كمان من البرزنتيشنز اللي كانت بتقدم على مدار ال3 ايام. فيعني انا متفائل جدا ان شاء الله بالفيوتشر بالحماس اللي انا شفته من الشباب. unpopular opinion، كل الناس بيقولوا روح اتعلم اي دلوقتي بقى بيكتب كود، فنصيحتي اتعلم ماث وساينس. اللي هي بريك ثرو في التو سبجكتس دول اكيد هو اللي هي بريك ثرو يعني. خلاص ده رأي شخصي باي ذا واي، لا يعبر عن اي حاجه، ممكن يكون صح غلط. على العموم انا بشكر يعني دكتور طه والمنظمين على الهاكاثون. شكرا جزيلا.
انا بشكر باشمهندس احمد، وبالفعل نصيحه غاليه جدا اللي بيقولها. انا طبعا عندي قناتين يوتيوب، واحده انجليزي وواحده عربي، واحده منها احنا بنتكلم في بودكاست كامل عن الحكايه دي. طبعا كان السي او في انفيديا يانسن كان يتكلم على الحكايه دي، ان فعلا الناس لازم تتعلم fundamental science in order to proceed not only coding، بس لازم يبقى عندهم domain knowledge. فدي حاجه كويسه. خلاص تروح بقى في الطابور. انت اتكلمت في رجاله، تروح هناك برضو. ماشي. دلوقتي احنا بقى في حد عندنا عبد الرحمن، هو اندر جراد منتور، هو طبعا الوحيد اللي معانا اندر جراد منتور. فعبد الرحمن عرف نفسك كويكلي وانطباعك في سطر واحد، يعني عايزين 60 ثانيه.
اوكي تمام.
هنا الفن.
انا عبد الرحمن البنا، انا اندر جراد اي. انا كنت مع دكتور طه من اول المانثلي سيريز للاي اي لاب للدراي ران هاكاثون للهاكاثون هنا، ومبسوط عامه بالرحله دي كلها، وبس ان شاء الله مكمل عامه يعني. بس تمام كده.
ماشي عبد الرحمن، انت خلصت تروح بقى هناك. ما ينفعش. مش عايزين بقى كل واحد فيكم يا جماعه هيعرف نفسه سريعا كده.
انا عمر صبحي. I'm part of the African Quantum Consortium. I'm very glad to be here. I started as a participant in the Dry Run Hackathon, and now I'm a mentor. يعني انا اكيد محتاج اقول ان المجهود الكوميونتي بذلوه من قبل حتى ما ندخل كمنتور وفي دراي ران، ومن قبل دراي ران فحقيقي هو مجهود عظيم ويشكروا عليه جدا، وانا شخصيا استفدت كتير. ويعني انا I can tell that all the teams here يعني have benefited a lot, so thank you very much.
شكرا عمر. انت خلاص تروح هناك مش نبيل؟
مساء الخير. انا محمد نبيل، حاليا في البري ماستر كمبيوتر ساينس في جامعه القاهره بباك جراوند كيمستري. والحقيقه انا مبسوط ان انا هنا، وطبعا يعني الحمد لله ان انا كنت مع دكتور طه من اول المشوار وبس.
شكرا جدا لكم. هو التيم حقيقه كله مجتهد جدا، فيعني احنا بنحاول نساعد كلنا بعض. مش عبد الرحمن، اتفضل معتز.
مساء الخير. انا اسمي معتز، انا واحد من تلاميذ دكتور احمد يونس في البروفيشنال ماستر في كوانتم كومبيوتنج، وسعيد ان انا جزء من التيم واقدر ان انا اساعد الشباب ان هم يحققوا اللي هم عايزينه يعني ان شاء الله. شكرا
جدا معتز. خلاص تروح بقى هناك. تمام، كويس انكم بتترصرصوا كده في شكل صوره عشان نبقى ناخدها في الاخر، فاهم؟ ده الهدف كان يعني. عبد الرحمن.
مساء النور. انا عبد الرحمن السيد، خريج هندسه اسكندريه كمبيوتر اند كوميونيكيشن انجينيرنج. كنت مع دكتور يونس في الجرادويشن بروجكت في الجي اي سيميوليتر. ان شاء الله دكتور يونس بقى هيتكلم عنه اكتر في السيشن يعني. وبرضه انا كنت من المنتورز المتاخرين شويه، جيت متاخر مع دكتور طه سليم، يعني كانت فرصه كويسه جدا، وان شاء الله بالتوفيق بقى في الهاكاثون.
شكرا عبد الرحمن. ماشي، اتفضل يا جهاد.
اوكي. انا جهاد سالم، خريجه AUC، كنت دبل ميجر كمبيوتر ساينس وماث. انا جويند هنا مع دكتور طه ومع التيم كله قريب قوي، بس اكتر حاجه حابه اقولها انه enjoy every single moment because الحاجات دي بجد هي اللي بعد كده هتقعدوا تفتكروها وهتحسوا ان دي moments كده في حياتكم بتحبوها جدا وبتحبوا ترجعوا ليها، فانجوي.
شكرا جدا ليك يا جهاد.
انا جمال منيب، اي اي انجينير. سعيد ان انا كنت مع دكتور طه في رحله الكوانتم اي اي لاب من الاول، وسعيد ان انا هنا النهارده بمنتور وبساعد الشباب في الهاكاثون.
شكرا جدا. واحب اوجه طبعا شكر خاص لكل، طبعا احنا عندنا طبعا جوري ممبرز وسبيكرز هتشوفوهم النهارده ان شاء الله في التوكس. هيبداوا من الدكتور هشام ان شاء الله لحد اخر اليوم. وبوجه تحيه كبيره لمكتبه اسكندريه على التنظيم، وعايز اوجه كمان شكر للاساتذه الافاضل هنا والناس اللي حضرت معانا في المانسلي سيريز. واحب اشكر برضو دكتور احمد شوقي على ان هو معانا، والدكتور شريف صديقي. واحب اشكر شكر خاص للدكتور احمد يونس، حقيقه بدا النشاط كله بتاع الكوانتم من زمان جدا، وعندنا سمرات هنا موجوده منه، فشكرا جدا لحضرتك. وشكرا جدا للناس اللي حاضره من منظمين المكتبه. احب اشكر بشكل خاص الباشمهندس يوسف الدكر، طبعا اخي وصديقي العزيز، وكان يعني بارتنر في الرحله اللطيفه، وهو كمان مع فريق المكتبه كل المجهود بيحاول يزق فيه لحد ما المومنت دي بقت بوسيبل مع كل البارتنرز المشاركين. شكرا جدا. واحب بس لو حضرتك تاخد لنا بقى صوره جماعيه كده ممكن. دلوقتي بيسعدني تقديم السيشن الثاني في الهاكاثون، وهو بيتكلم على الكوانتم يوز كيسز كوانتم ابلكيشن. وطبعا يشرفني ان انا اقدم استاذنا العزيز الاستاذ الدكتور هشام البدوي. الأستاذ الدكتور هشام البدوي هو he's a full professor since October 2013 in the area of network performance modeling and assessment techniques for wireless cellular networks. Since 2004 he has been an adjacent professor for mobile communications in the Arab Academy of Science and Technology. He also has more than 32 years of professional experience in the fields of mobile telecommunications, network infrastructure, and has held various engineering and managerial positions. ودكتور هشام حاليا هو رئيس وحدة التطوير والابتكار بوزارة الاتصالات. بيشرفنا جدا الدكتور هشام، تحية بقى كبيرة ليه. اتفضل.
السلام عليكم. Today we will talk about in this presentation about the new trends, challenges, limitations, and opportunities that may face one of the most attractive application from my point of view for the quantum technology. Especially we can say QSC, quantum safe communications. And also finally we will mention some sort of research directions or open areas in the development and implementation as well as the realization of such technology in the field of applied safe communication facility. The contents, as you can see, by the way, I am also the vice chair for the Egyptian IEEE Egypt section, as well as I am the chair for the vehicular technology chapter. And the quantum technology has a long penetration and huge penetration in the IEEE community, especially in the field of application looks like vehicular technology, wireless communications, and AI as well. Today we will talk about, first of all, the quantum cryptography, and then we can move forward to the most popular types, which will be discussed later, post-quantum cryptography, and then we move forward to QKD, as well as quantum random number generators. Then we will sum up all of these in the field of application of the quantum safe communication networks. And finally, we will highlight some sort of challenges, opportunities, as well as some sort of new research directions in this field. First of all, quantum cryptography. Quantum cryptography, as you can see from this very simple diagram, now we are moving or using the regular or classical encryption technique based on hash function or some sort of multiplication with special codes or something. This is called classical cryptography. The quantum cryptography will talk about some sort of deploying or use of the facility of quantum physics or quantum polarization, as well as quantum algorithms, in order to have some sort of encryption and immunity to regular classical decryptor systems. Also in these days, all the operators or all the players or stakeholders are deploying what we called harvest now, decrypt later. So if you don't have enough computational power, now it's your opportunity to save all what's going maybe on the internet, on WhatsApp or something, and then if you have enough computational power such that mature quantum computing, which will be maybe in 2029 or 2030, you can decrypt them very easy, and then you can have some sort of interception, as well as these powerful computing machines can decrypt all of them. So it makes some sort of threat or some sort of dangerous attacks to all our communities. Quantum cryptography poses the processes of how to protect against theoretical threats for public key distributions, especially for symmetric key and under research asymmetric key. Also, this came to real world by the deployment of the Peter Shor's integer factoring algorithm that had been deployed in order to break or decompose the regular functionality and algorithms based on RSA or Diffie-Hellman as an example. From the point of view of quantum safe communication, we have to think about what we call quantum key infrastructure. This will provide some sort of safe communication and can provide some sort of vaccine or anti-threat methodology for the classical as well as the quantum computational attacks or threats. This will have some sort of expenses, but practically it will save a lot. If you cannot protect your data, you will lose everything. So we can say that it is cost effective in spite of the real cost. You have more reward or more beneficial for such deployment. Also, it can use VPN and protect what we call cloud data, mobile communication, special attacks will be considered for the field of wireless communication facility. So we need for quantum safe communication not as some sort of luxury, but it will be a must for all now, today, not tomorrow. In order to protect our data to be stolen or decrypted, maybe next year, maybe next month, so we have to think about how could we protect them now. Also, the internet is evolving very fast, and we have some sort of what we call quantum internet technology, so it will be more immune to interception or penetration or threats or attacks. On the other hand, we have to migrate to the quantum communication facility in order to have some sort of protection. If we are going to compare what we have and what we need, practically we have to think about, on the right side by the red color, unsafe cryptography, which is used nowadays, which is the deployment of classical cryptography, which is based on long keys, maybe AES or RSA 256512. It may take now maybe thousands of years to be breakable, but by the deployment of quantum machines, you can break it in few seconds, maybe in 2030, as I said before, and maybe before this date. In the field of how to protect yourself, you have to think about quantum-resistant cryptography, which is based on two main solutions, which is the PQC, as we will illustrate in the next slides, and the QKD, and finally the quantum random generators that will facilitate the opportunity and realize the immunity to threats or attacks, or at least decrease the opportunity or the possibility of decoding or decrypt your data. So in order to realize the quantum safety, we have to think about three main steps. The first step is post-quantum cryptography, or what we call PQC, which is based on mathematical algorithm, not hardware. It's just some sort of mathematical manipulation of special functions in order to achieve some sort of semi-classical cryptography, but it can be immune, maybe enough to concurrent classical attacks. On the other hand, quantum key distribution based on hardware deployment as well as software algorithms in order to protect your data based on the principles of quantum mechanics and the quantum technology. Finally, quantum random generators will be the future, near future. It is based on hardware and software that not use unique keys. These unique keys cannot be breakable by classical or regular quantum machines. First of all, let us talk about post-quantum cryptography. Post-quantum cryptography looks like classical cryptography based on mathematical foundation, but it will use some sort of special functions and special protocols. And by the way, this hackathon is some sort, maybe I hope, to be some sort of imitation or maybe on the same roadmap to what has done in the US by NIST. In 2016, they announced that they have some sort of hackathon for special algorithms for PQC between developers, programmers, researchers, or engineers in order to achieve some sort of interoperability and stability against localized attacks. This hackathon had been contributed by maybe more than 113 teams, but about 5 only has gained the prize, but these prizes has been changed or converted into public or by law encryption methodologies by 13th of August last year to 2024. and announced by NIST, and it will be by law to be used for the IoT services in US. And this is NIST, and this is the final 5 teams that had been transferred from just, as we said here, hackathon means some sort of contest, think, trials, success, failure. Now they change it into small emerging companies to deploy such technology. And the main algorithm families are lattice-based and the cloud-based, and also multivariable-based, as well as hash-based. Let us take some sort of comparative analysis between these systems. For this table, no more equations, but think about, they are talking about module learning key encapsulation mechanism. It's based on lattice-based, suitable for the encryption key exchange, and it has some sort of balancing or equiprobable between the trade-off between your speed of calculation against security. Also, the DSA, or digital signature algorithm, which is one of the main players in the financial protection systems, they have 2 lattice-based systems, one of them based on long keys, and one which is FNDSA is used for short keys. On the other hand, hash-based and the code-based maybe looks like Hamming, quasi-cyclic. This is provides cryptographic diversity and they can protect you without hardware. This only for deployment based on software on your concurrent legacy networks. If we are comparing PQC system versus classical system, we can catch the point. On the left hand, classical cryptography, you have end-to-end encryption or not end-to-end encryption, looks like Line, Viber, WhatsApp, Signal, iMessage, and so on. On the PQC, you are inserting some sort of algorithms in order to protect or convolute your data by a way to protect them. Looks like the future of PQC establishment and how could you make it for authentication processes. On the other hand, now we are moving forward to what we call quantum key distribution, which is based not only on software algorithms, but as well on special hardware. And by the way, it is a cheap type of hardware, maybe $100, 300, 1,000, not more. Looks like quantum processors, which is by millions of dollars. Quantum key distribution, which is called abbreviated by QKD. QKD is used heavily for fiber optic communication facility. Looks like what had been done in Europe or China for protecting the railway systems. By the way, in China, they have now 20,000 railway QKD protected interconnecting system to protect the railway from accidents and speed limits. The evolution of QKD, as you know, it was started by first protocol, PPP-PP84, and go to the what we call the Quantum Safe Security Working Group, which is developing the solution based on quantum technology, hardware, and software. And the market size is going very fast, and maybe now we have more than 20 vendors for such modules that may be inserted before your classical encryption and before and after your classical decryption. By deploying the quantum key distribution, you have the opportunity to secure your data by special key exchange, and you have some sort of real-time application for your security. The process of quantum key distribution based on very simple item that comes from the legacy or the history of the quantum. The quantum, as you know, it's some sort of ambiguity. If you don't have the 100% percentage, do you know that you have the situation or the probability of having 1 or 0, and this is presented by polarization. And by changing this polarization, you can transmit your photons. If some eavesdrops coming into the inside as a man in the middle, it will change the polarization, and this will help the receiver to identify this is some sort of intrusion. And in this diagram, in legacy system, if you are transmitting from Alice to Bob and Eve and the man in the middle, if you are transmitting 101, Eve can easily, especially in wireless, have some copy of your RF transmitted signal, and they can decode it very easy. But in case of QKD, we have sort of this diagram, very simple diagram. Alice wants to send something to Bob by quantum state preparation via quantum channel or fiber channel, and they have some sort of pre-assigned keys to be transmitted and verified over the authenticated classical channel. And in this diagram, if Eve wants to just listen on the quantum channel, this will interrupt and make some sort of ambiguity of the polarized received photons in the pop side, and this will affect the overall behavior. So pop will determine that this link is not secure enough and will stop directly the transmission. And this is called non-cloning facility or non-cloning theorem. It will provide some sort of protection of your transmitted polarized signal, and can be detected easily. If you don't protect this, you will lose the polarization, and then we can say that this link is not safe. Quantum key distribution use cases, so many use cases. We can look at healthcare, quantum cryptography for 5G and 6G, Internet of Things, government, banking, or financial inclusion systems, also smart grid for power distribution facility. For vehicle communication has some sort of very, very dangerous case, because in the vehicle intercommunication or V2I network facility, if you got the transfer or the data that had been transmitted over the air, you can destroy or change it, so the interoperability between cars will be decrypted and may be changed, so some sort of error will be done, or crash or accident. So one of the trials maybe had been deployed or experimented this year by last February. It was in the FSO OKD transmitter and based on free space optics, and this had been successful results. For the QKD secured V2I systems, this is a global vision for how to deploy or implement the ITS or Intelligent Transportation Facility for interconnecting vehicle to vehicle or vehicle to infrastructure based on QKD. And as you can find in this diagram, QKD is just an layer 2 device, just to be inserted in your network on both sides, so you can protect this network against regular threats. Types of QKD protocols. The protocols of the QKD is divided into two main categories: prepare and measure group and intelligent based. Prepare and measurement involves measuring states of a particle. Intelligent based depends on exclusive quantum intelligent, and the measurement actions may be done over one particle. If we are going to summarize the comparison between the most commonly used in QKD. We have BP84, E29, MDI QKD, and device-independent QKD. We have key features, strengths, and limitation. As an example, for the BP84, which is the most popular one, it is simple and susceptible to side channel attacks, which will be solved in our next section. Okay? In E29 and E91, sorry, it's reliable, require reliable integrment generation and measurement, but MDI QKD is more complex than the BP in price of protecting your feedback key distribution channel. What about the challenges of the QKD? The challenges mainly how to merging it with your present or ongoing infrastructure. Also, the transmission range is not tested more than 100 kilometers. So it will not be suited enough for long distance ITS or for satellite facility. Also, QKD has some sort of problem of how could you protect the key distribution process or initiation process itself. If we are going to facilitate the PQC or QKD, we have to think about from the larger vision, how could we make some sort of head versus head or head-to-head comparison. If we are talking about PQC against QKD, because these technologies are already found in the market, okay? Security based, as we said, PQC based on mathematics or just software. QKD based on quantum computational technology based on software and hardware. The cost is very low for PQC and may be very expensive with respect to it in the QKD. Maturity, QKD is most mature than PQC because it is more stable and have a lot of trials. From the possibility of deployment, PQC for internet, software, cloud. But if we are going to have more and more sensitive application, we have to think about QKD in place of PQC. If we are going to the near future, we have to think about how could we going away from single key or single key distribution, which is one of the limitations of the QKD. Quantum random number generators has some sort of this solution in order to provide strong randomness and enhanced security by changing the key periodically. So if the key 1 is decrypted, the key number 2 will not be decrypted and so on. So you can use it for securing the blockchain and 6G applications. Quantum random generators already has some trials, not commercial. Looks like these processors. It is used not only for classical cryptography, but also for ongoing facilities. But they need huge investment plans. If we are going to the deployment of all of these technology to have what we start our talk today about, quantum safe communications, quantum secure direct communication is one of the underdevelopment technology that may be used to enhance and correct the error that may be caused in the QKD by protecting the key distribution technique that had been mentioned as one of the drawbacks of the QKD. QSDC, which is quantum secure direct communication, completely very, very effective as an idea in 2000, but nowadays it may be standardized in next few years. QSDC characteristics maybe summarized in 3 points. Higher safety with respect to QKD because it is not used for using one quantum key. Also, no need for pre-assignment key, so the listener or the intruder will not know the initiative point, so it can work on it and it can extract or predict or estimate what is the key of the QKD. Also, it is suitable for high capacity communication facilities, and this is very, very suitable for sensor networks or what we call quantum sensing applications. QSDC security protocols has some sort of success stories for protocols. Looks like DL04. It has 18.5 kilometers and data rate up to 100 kilobit per second. Somebody will wonder that 100 kilobit is very small. 100 kilobit per second is very suitable for IoT application. Looks like control and signaling schemes. So it will be suitable for such technology, and the QKD may be deployed under the QSDC for high-speed or wideband applications. One of the major applications of the QSDC is the time-sensitive networking, which is deploying for providing low-latency application. It looks like remote surgery or remote control system, high reliable communication, synchronization facility for vehicular to everything or vehicular to V2X, also the realization of the intelligent transportation system, as well as power distribution facility and power monitoring for smart grid and power control, also the integration between TSN and 6G. If we are talking about how to combine QSDC and TSN, we have some sort of collaboration as direct quantum communication. Also avoid the complexity of queue management, because if you are using a simple key, your network will be breakable. So all of the quantum safe communication comes to have some sort of adding some sort of higher security or higher immunity. Also, it will simplify the network infrastructure and enhance anti-attack methodology. If we are going to talk about the QSDC and the QKD versus the classical TSN. From the key management point of view, no need for key management for QSDC. QKD, one of its main bottleneck, you have to require some sort of a strict key distribution methodology. And the TSN or classical technology requires relative complex key management infrastructure. The latency in QSDC is low. QKD, in order to have or achieve the interoperability of safe channel, you will pay higher latency. Scalability, QSDC is some sort of expandable network, so your network can absorb or can accommodate huge number of players in your network. QKD, according to the limitation of the limited number of secured keys, you have some sort of limited scalability. The impact of QSDC on TSN, QSDC will not enhance the TSN only, but it will have some sort of more security, small latency, large scalability, and the special time synchronization because of the high speed application looks like 6G and so on, requires very, very strict time synchronization. And it has some sort of looks like a P2P protocol, and network complexity may be reduced. If we are going finally to the challenges, opportunities, and research directions, we can see this. This is a timeline. I get it from NEST this year about the year of the development. As you see in the green line, PQC started from previous and keep going. QKD come to be in the same field, but symmetric key cryptography is already under break. And maybe asymmetric key, maybe as we said, 2030, it will come true to be breaked. Challenges that we are facing in the quantum cryptography in large, cost and scalability issues, which has been solved by QSDC. Vulnerabilities in quantum system looks like fault error control, or temperature effect, or vibration effect, and I think this may be solved or undergoing to be solved by the development in the quantum physics. Regularity, and this is a very important point, if you are going to deploy network, you have to same sort of control or regulating it. So regularity and the standardization process have some sort of challenges, and the quantum have some sort of what we call transient state, which is called quantum hybrid security solution. Quantum hybrid security solution looks like two steps. First step, if you have to deploy some sort, looks like key mixing, by mixing between the legacy key or classical key and the quantum safe key, which is QKD or PQC, and you can merge both of them in order to have some sort of protection with minimum cost or minimize the cost hybrid quantum safe key for symmetric encryption. If we are going to financial inclusion system or financial application, we can think about the hybrid solution for dual signing certificates by merging the quantum safe signature and the legacy certificate in order to validate the signature of the user, and can facilitate the banking efficiency and safe communication in the near future. R&D direction for quantum hardware development, we have to think about how we can extend the scalability of the system, how we migrate our quantum safe communication to serve as one of the major players in the telecom industry, and on-chip integration to merge between the CMOS-based and fiber or optic-based hardware in order to have the beneficial of both of them. And in the near future, we will change the think about or the principle that previously we were using the processor as CMOS-based or electronic-based, and the interconnection or interoperability, it was based on optics. In the near future, it will be changed. The calculation will be based on optics, and the control will be based on electronics. Also, in the R&D direction for quantum software development, we have to think about, as today's hackathon, as a small version, develop specialized quantum software. Also, open source, use of the open source, looks like Quix of the IPM or Qubit for another vendors, to design and optimization of the generation of photonic graph states. Also design tools tailored to noisy intermediate scale quantum era. Finally, if we think about what will be the challenges that we have to tackle in this era, we have signal attenuation. The fiber or the optic signal is attenuated in the system or during the propagation, so we have to improve the error correction facility. Noise and interference, we have to make some sort of mitigation or fault error control mechanisms. Also think about the scalability and hardware limitation, as well as the standardization. From the standardization and regularity point of view, this is the last slide, okay? Sorry for long talk. We have interoperability. We have to unified scheme, because in the telecom network, your network must be interoperable or can be detected and integrated easily to accommodate other devices or other facilities. Also security benchmarks by using minimum key lengths in order to minimize the overhead and increase the overall system throughput, as well as the hardware requirements and regularity compliance, and for sure ethical deployment. Finally, the conclusion is quantum threat is real. Now we have to move on, not tomorrow. BQC, primary solution, most efficient, cost-efficient solution, but not fully protected. QKD offers good security perspective, but in price of key distribution mechanism and how could you protect it. QR energy is the near future, and the QSDC is the solution for control the time-sensitive application. The future is using the hybrid in order to conserve the investment that had been done in the legacy or classical networks. And also we have to start planning to quantum safe migration now. Thank you.
شكرا جدا لدكتور هشام على التوك الرائع ده. لو في اي اسئله، احنا عندنا دقيقه واحده بس للاسئله او سؤالين. We have 1 or 2 minutes for questions. Also you can feel free to do so in the lunch break. And now we have Professor Dr. Ahmed Shawqi Musa. Dr. Ahmed Shawqi is going to present HPC and the QC Nexus, Genesis and Prospects. طبعا تحيه كبيره دكتور بقى احمد شوقي، كان استاذ بقى في الاندر جراد وراجل منتور، يعني مش عايز اقول لك يعني فضل منتور طول الحياه. It's not only for undergrad but it continued even till today. Dr. Ahmed Shawqi Musa is a professor of computing and computational sciences at the Faculty of Computers and Artificial Intelligence, Cairo University, where he is also founder and head of the HPC R&D lab. He also served as the HPC director at the Applied Innovation Center of the Ministry of Communications and Information Technology, where he founded and led the first HPC system at MCIT. Dr. Musa's main field of expertise is HPC and its integration with various AI paradigms to create computationally intelligent HPC systems in both the academic and industrial worlds.
شكرا جزيلا. Thank you. Good afternoon. Thanks for the experts who spoke before me because they saved me some time. I will not be talking too much. Dr. Hisham and Dr. Taha actually in their talks explained some concepts that I was planning to spend some time with. Now I don't have to, so thank you again. My talk today is about the nexus or the connection between the high-performance computing and quantum computing. I'm mainly in the field of HPC, high-performance computing. But I got introduced or started my journey with the quantum computing journey in around 2001 or 2002. It was mere curiosity. I took a course at Florida State University at the Department of Mathematics on quantum computing and quantum information. At that time, there was no quantum computing systems deployed or envisioned to be deployed any soon at that time. So I think quantum computing has the unique case when the science developed much ahead of the technology. And until today, this still holds. To start with a quick introduction, what we see here is, or was, the fastest computer in the world, the strongest high-performance computer in the world in 2009. A few years later, RIKEN, National Laboratory and University in Japan, in cooperation with Fujitsu, developed the fastest computer in the world. I think it was 2011 or 2012. It is K computer, the one that we see right now. I'm skipping many computers in the middle. After that, the first computer in the world became Fugaku, which was also developed by RIKEN with Fujitsu. And it didn't last as the fastest computer in the world too much because, by the way, the people who developed this are the people who developed Fugaku. And it didn't last much because there was much need and a big competition for speed in the computing systems. So Frontier became the first EXA scale. EXA means a computer capable of performing million trillion floating point operations per second. So this became the first exascale computer in the world, and I will say in a minute why. Now it is not the fastest computer in the world anymore. El Capitan came after that to become the fastest computer in the world, also in the United States, of course, in the exascale computing system. And by the way, in the middle, some computers got into the exascale, but they did not list as the fastest computer in the world. They didn't get the chance to do that. By the time they were able to deploy their computers, they were not the fastest computer in the world anymore. If you want to see the list, it is actually on the top500.org. It is available in public. You see here that Aurora, number 3, is also in the exascale, but it never listed as the fastest computer in the world. And you can see the whole list. The speed or the competition, the race for the exascale computing started like around 2010. We can see here in the news from 2012, IBM announced that we must, not we have to, we must have an exascale computer by the year 2024. And then they tried to make it by 2028 because they couldn't wait. And they failed, they couldn't. And then they tried to make it again in 2020. And finally, they got it done, but other computers were in the race. We see here that this is an executive order, and this is the reason, by the way, these computers got into the top of the exascale, and the other computers were in the exascale, but did not catch the first place in the race toward the fastest computer in the world. This is because the United States issued a White House executive order, because they consider the speed of the exascale computer, the computer who is capable of performing million, trillion operation per second, was for them a matter of national security. President Obama spoke about it publicly, and he said, it is not that the United States is going to obtain the exascale computer. The United States must be the first country to obtain the exascale computer, because every day we are not number one, takes us back behind tens, maybe hundreds of years behind the number one. So this is why we can see here that these computers are now, the top 3 are all American, but other countries are still in the race, and we will see in a minute what happens. So what is HPC? It is the classical computer theory we applied. We developed a program. The program must run in the zeros and ones, the binary system. Now the binary system is too large and too complex to develop, so we have like an assembly language to have the machine instructions executed, and we have high-level languages to develop those, and programs in between, like the compiler and the assembler, develop the programs that will run on the computer. Now, the question is why HPC and why exascale? If we want to develop a program like the one on the screen, which I think any student sitting in the hall now can write this or know what these 2 lines of code in the C language are about. This is a loop that if we want to run a program to run trillion times in a second, we have to get these 2 lines to run in 1 second. That means we want the hardware to make 3 times 10 to the 12 trips. Trips between what? Between the memory system and the processor. This is the way the classical computer works. So we will have like 3 arrays. Each array is a trillion elements, and they will be in the memory system. And what we have here is the processor. So we will get the first word from the memory to the one of the registers in the processor, and then we will get another word from the memory to the processor, and the processor will do the calculation, and if the calculation is not stored in the memory system, it will be lost. So these are the 3 trips. We want to make these 3 trips trillion times in 1 second. Scientifically, from the physics, we know that this is impossible. Why? Because, you know, speed goes with the distance, speed, and the time. So if we want to make 3 times 10 to the 12 trips in 1 second, now we have the time and we have the distance. Now, what is the distance between the memory and the processor that would enable us to accomplish this? We have the speed, even if we assume that the speed is the speed of light, which is not true. It's an exaggeration, but let's go with this exaggeration. So we have the speed and we have the time. The distance must satisfy this equation, which is going to be translated into a word size fitting in something times 10 to the minus 10 meters. 10 to the minus 10 is the size of a small atom. It is not the smallest atom, not the hydrogen atom, but it's the size of the small atom. So until comes the day when we are able to fit 1 word of memory into a single atom, even if it is not a small atom, until that day is come, this calculation by a classical computer, even if it is a supercomputer, is physically and scientifically impossible. Now, let's assume that it became possible somehow. In that case, we are fitting a word into the subatomic level. Now, the binary computing doesn't hold. The electricity of the Maxwell equations don't hold anymore. Now we are in the quantum world. So we need to migrate into the quantum world to do that. Of course, these big speeds made huge transformations in the practice of science and engineering. In the past, the science used to be theoretical or experimental. With the high-performance computing and the supercomputers, now it became computational when we don't have a theory and it's impossible to do the experimentation. And in the modern days, this led also to what we call the data-driven science, when we don't even have a computational model to perform. So we have to extract everything from the data that we already have. This huge transformation and this expectation that things will be miniaturized, it will become smaller and smaller until they fit within an atom, led to the thinking of the possibility of using the quantum system in computation. And this made many people, including myself, think that maybe the quantum computing is the future of the computing. It is the next step after the HPC systems. And after getting into that for years, studying it and working with it, I'm coming today to say that this is not true. It will not happen this way, but quantum computing is very important. Now it is time to thank Dr. Taha for making this introduction about the difference between the bit and the qubit. I don't have to explain that anymore, so my talk is going to be shorter. Good news for you too. As you know, in the classical world, the bit is either a 0 or 1 and nothing in between. But in the quantum world, there are things in between. So it can be superposition, which is a good news. Why is this a good news? It's very simple, because when we have a classical bit, we have combinations of 2 numbers, zeros or 1. But when we have quantum computing system, if we have 2 qubits, 2 bits of the quantum type, then we have combinations of 4 numbers instead of 2. But the difference between 2 and 4 is not that big. True, but as the system scales up, we can see that it becomes huge. See here that once you have 3 qubits, now you have the required bits to represent that in classical becomes 8, and this is 1 byte. But by here, you can see that n qubits is 2 to the n classical bits. So 300 qubits becomes 2 to the 300 bits. This is a huge number. Until now, it is impossible to implement it. This actually opens the first nexus between the HPC and the quantum computing system, which is what we call the quantum parallelism. Quantum computers are parallel by nature, because when the computer is processing, it is processing different combinations simultaneously in parallel. This is what we actually try to do in the high performance computing, in the parallel system. We try to deliberately get the computers were not like that in the past. It was one processor running one instruction at a time. But now we are trying to get it to process more parallel instructions at the same time. But quantum computers are by nature parallel. But there is a price for that, is that the computing is not reversible and not stoppable. We cannot get in to see what is going on and get the intermediate steps in the middle. So we can get all these bits to work together, but we have to wait until it finishes to see it, because we cannot detect the superposition. Once we detect it, it's lost. We cannot build on the intermediate steps. So this is the first nexus between the two. Quantum computers are parallel by nature, but they are not stoppable, and we cannot get the intermediate steps. We have to complete the algorithm until the end. Of course, there are other things. So here, this is about the difference between the HPC and quantum computing system. As I said, many people ask if quantum computing is the next step. I would say, no, it is a next step, but not the next step. So the HPC is going to continue. What we see people issuing executive order from the White House, spending billion, maybe trillions of dollars on HP system. It's not only for the next 3 or 4 or 5 or even 10 years. It is going to last, and it is going to develop, as I will show in a few minutes. Is quantum computer superior to HPC? No. They actually excel in different types of problems. There are points of superiority for each one over the other. Plus, we are not going to see like smartwatches and phones in our pockets based on quantum computing any soon. So this is another point for classical computing system to last for at least tens of years from today. Okay, so what is next? As I actually, coming from the HPC world, I expected that there must be, I started investigating myself before I found out that actually other people are thinking about that. High performance computing is implemented by many paradigms, including algorithm, mathematics, and many things, but its main focus is parallel computation, how to parallelize the computation. So as coming into the quantum computing world from the high performance computing world, I started myself thinking, what about connecting quantum computing systems to run in parallel? They run in parallel internally by default. We can think of that like the multi-core today. Many cores are running on the same processor at the same time, but this is not enough. So what we do, we connect processors which are composed of different cores to run together, so we have like larger number of cores running on the same problem at the same time. And it turned out that actually this is what the world is doing. So what we see here is some sort of news about the high performance computing regardless of the quantum computing. Japan is working now not on the exascale computer, it is working on the zeta scale computer. Zeta means 1,000 exa, which means billion, trillion operations every second. And I'm not talking about any quantum computing systems in here. And they're close, by the way. So the world thinks that it is the United States and China that are racing in the high performance and exascale. No, actually Japan is working silent on something else, and this computer is very close to deployment. On the quantum computing side, we spoke already about the quantum parallelism, but the world is working in many directions. As our professors Dr. Hisham, Dr. Ahmed, and Dr. Taha spoke about, the hardware development is moving in different directions. There are several hardware technologies to develop the quantum computers. Well, they are working on it. It is still, the number of qubits is still the main obstacle. So in the near future, we expect that IBM is going, they said in 2033. I don't know, maybe they try to come with it sooner. They are going to have like 100,000 qubits computer. They said 2025, they were going to have 4,000, a bit more than 4,000 qubits. I don't know if this is already released or not yet. But anyway, trying to increase the number of qubits is very important, because by the time we reach the number 1 million qubit, now we are in the post-quantum computing, post-quantum cryptography era that Dr. Hisham was talking about. This is what we are waiting for. And this is why they are developing from now algorithms and solution for post, which means after the deployment of the 1 million qubits. China is working in a different direction, trying to make appliances of the quantum computing systems. So now they sell these small quantum computing systems. One of them was obtained at the American University in Cairo, I think 2 years ago, working on it. So I don't want to spend much time talking about this because the news are all over the internet. But what I wanted to introduce here in the Nexus is the genesis of the Nexus. I said that we were I started thinking about why don't we make several quantum computers connect together and run in parallel. Actually, Japan is actually doing that right now with IBM. Together, they started working on developing a parallel quantum computing system to work together. Now, how is it going to work in parallel? Like, is it going to connect several computers? Are they going to connect them from the port side? No, actually the parallelism here is more important because it's on an instruction level. So they want the instructions to be running in parallel between a high-performance computer and a quantum computer working together. So not two quantum computers working together. Actually, they want to connect the new computer being done by RIKEN also, along with Fujitsu. They wanted to run with a quantum computer to work together. And in this case, this opens a whole new paradigm for programming the system, because the current languages and the current algorithms now are either a quantum or classical. Now, if they work together and we have instruction level parallelism between the two, now we need to think of completely different algorithms and programming languages and programming paradigms to be able to create one program that will run on a quantum computer and on a classical HPC computer at the same time. This is a whole different from what we are talking about. So I hope I made the case that not one of them is going to like replace the other. They are meant to coexist, and the coexistence is in the genesis. It's in creation right now. Japan is not the only country working on that, but I think from what I read, they are the most advanced. As I said, it's algorithms at new scale. We must come up with different algorithms. Like when we learned about quantum physics and we wanted to use quantum physics for computation, we had to think of different algorithms, different way of thinking, because the classical algorithms are not going to work on the quantum system. We have to think differently. Now, again, we have to think differently when we connect the classical with the quantum. They are not going to be one replacing the other. We need to fuse them, and we need to learn how to fuse them. In conclusion, the two systems are going to coexist and are about in very few years going to open new paradigms for programming, for the industry, for development, for everything. And we are going to have quantum HPCs and HPC quantum systems coexisting together. The two systems run completely different theory of computation, but they still have the same theory of computability. There are problems that are not meant for a computing system. They are by design or by definition uncomputable problem. Those remain uncomputable by the quantum computer. Quantum computer in some problems is going to perform much, much faster. Like Dr. Hisham referred to that about the cryptography. Using the current algorithms for encryption, classical supercomputer, the fastest in the world, may take millions of years to encrypt, to decrypt it. Quantum computer is going to decrypt it like in few minutes or even in few seconds. But other problems are still not to be solved by quantum computer. They will have to be solved by the HPC systems, and this is why the advanced world is actually working now on connecting them together to write a single program that runs both at the same time. That's different, and that's what I wanted to say. Thank you.
Thanks very much, Dr. Ahmed, for this wonderful and nice talk. We have 1 minute or two for questions. We have questions. Yeah,
yes.
Please.
It was mentioned that quantum computers have an advantage in certain problems, and the classical computers have an advantage in others. But I'm asking, are there a set of problems that are equal for both quantum and classical computers that are in the future? If quantum computers are now limited by the noise and the 0 Kelvin limitations, and the HPC are limited by Moore's law, and they are going to require more massive structures to gain more powerful computation. In such problems where there are no quantum advantage, which would be easier engineering wise to be industrial to have, like a massive HPC or a quantum computer with 0 Kelvin temperature to solve this type problems?
Well, excellent question, but very difficult. I don't know if I will be able to give a conclusive answer, but let me refer that the answer to that is actually the last thing I said. One point in your question, you mentioned Moore's law. Moore's law doesn't hold anymore. We know that. And even in classical computer, we reach a technological limitation because of the power voltages. We are unable to make the voltage differences any smaller. Consequently, we are not able to get the processors to be higher frequency. And this is why we went to the parallel cores or the parallel processors to compensate for that. So this is an obstacle on the HPC world, and you mentioned some obstacles on the quantum computing world. In one direction, we are trying, not we, but people are working on trying to solve both, find ways around those. But as you can see, we are hitting walls. These are physical limitations. Unless you find new physics or new material or something, we are unable to overcome these problems. And in this case, this is actually one of the reasons the fusion between HPC and the quantum computing is created. Because this is not going to be able to solve it, or maybe we'll be able to solve it in millions of years. We cannot wait millions of years. And this will never be able to solve it on the scale that we need, at least not for tens of years from now. So what is the solution? Combine them together. This is what we do. And with some AI, but I was trying to avoid the talk about AI because AI now looks like limited in the minds of many people to be machine learning or deep learning. It is much more than that. Doing approximate computation along with the HPC and the quantum computing system may be the ideal paradigm for dealing with the problems of the type that you mentioned. I hope I gave the answer at least partially acceptable.
Thanks, Dr. Ahmed again. Okay, big clap to Dr. Ahmed.